hand it off to Millen to kind of start us off.
So, quick overview about the project. We're EVC autonomous, and our goal is to build and race a fully autonomous electric go-kart. Our target event is the the Autonomous Grand Prix held after finals week in May, which takes place at Purdue Grand Prix track. And our system is especially designed for this track, and that's our target. So as for what we're doing for the kart itself, we're using a standard go-kart chassis, and then we're mounting a servo instead of a steering wheel so that we can steer the kart. We have a STM32 Nucleo board, which is going to control the electronics, a VESC motor controller, which will drive the motor, and up to 5 Rubik Pis, which Qualcomm has gave to us, and that will be our main software. And then in terms of sensors, we're planning on having at least 1 camera and GPS. And then we have physical brakes. However, for the short term, we are planning on using just like setting speed to 0 with our motor and regen braking. So the goal of this design review is we're going to tell you what we're doing, and you're going to tell us if that's a good idea, a bad idea. If you have any clarifying questions or comments or general concern, please tell us. We're especially looking for feedback on our overall system design, our 3D GS pipeline, which Shai will talk about more later, our live calibration system, the general performance, because our goal is to run all the software on the kart in real time, as well as how to best make use of the fact that we have multiple Rubik Pis on the kart and being able to split work amongst them effectively. Give just a really short context. The electrical for the kart is, in terms of the software, the goal is it's as simple as possible, with most of it being handled by the Rubik Pis. We have STM32 Nucleo board that's going to be responsible for issuing the commands to the motor controller and the steering servo. It'll communicate with the Rubik Pi via SPI. And as of right now, we currently have it communicating with the VESC motor controller via PWM. But in the future, that'll probably switch either CAN, UART, or SPI. And then in the future, as well, one of the things we're required for the Grand Prix is to have remote control as a safety feature, both as a force like remote stop and just general driving of the kart. So that's also planned.
Okay, so to start off, for our people on the meeting, we can't see the chat, so please just feel free to interrupt if you ever have any feedback or any questions, anything to clarify. But we're basing our approach on a very popular F110 strategy, where we have 3 different loops. One is a fast loop for making corrections. We have a medium localization loop and a slow calibration loop, which provides updates. As Millen previously established, we have cameras and GPS, and we output motor and steering. So to give a little bit more context on the software stack, here is the loops that we're planning on running. So the driving loop is going to run at 60 Hertz, and essentially how it works is it takes in the camera input, is processed by the OpenCV team, and they're going to talk about that in a few minutes. And then that's passed to the Pathfinder, which the Pathfinder team will talk about, and we output motor and steering commands. And then if we take a look at the calibration loop, we see the corrector, and so if we're off of the expected pre-computed race line, then it will add bias or will add a correction to the Pathfinder to make our way back to the expected line, and the calibrator will make note of that. And so the calibrator will, in real time, update both the kart parameters and add a permanent bias multiplier to make sure that if we're consistently overcorrecting or consistently undercorrecting, then we fix that. Next, the localization loop. So this is just an extended Kalman filter and the 3D Gaussian splatting localization pipeline that we're going to talk about. And that's queried by the calibrator and the corrector to figure out where we are with the covariance matrix. So I'd like to invite up the OpenCV squad to quickly give us a rundown. Okay, then I'm just gonna talk about it for you guys. So how this pipeline works is we just want to quickly figure out where we need to turn. And this is running very, very fast, and the rubrics aren't super efficient. Actually, we have a rubric right here, and if you want to kind of pass that back. But how this works is it takes in an input from the camera and it processes it, and so it figures out the two angles to the racing line, as you can kind of see here, to the racetrack. And then from that, we can let the Pathfinder give arguments. So that's kind of a rundown. I'd like to invite up the Pathfinder game to give a few words.
Right, so my name is Hrithik, and I've been working on like the pathfinding, determining like where the car should go on the track.
I'm Sahil and I've been doing the same. So what we've been doing recently is developing the logic for the angles for the cart's turning and the degree it's turning. So what we've been doing is averaging the left and right angle, and that is what we've been using to determine how much the car should turn, as well as we've been determining the cart's speed, and this has been using the model with 30 miles per hour on the straights and 50 miles per hour on the turns.
And our next steps, well, is first to optimize the racing trajectory, and we'll do that by like using a model predictive controller, which will like have a better path like that isn't just the middle of the road. We'll have an actual racing line, and we could like complement this with a PID style logic so that we can like have smoother steering inputs and smoother acceleration inputs. And if we get all this right, we also want to like account for other vehicles on the track as well, so it can maneuver around like other vehicles or debris. We're probably gonna use like YOLO object detection, but to be honest, this is all like subject to change. That's about it.
Thank you, guys. So next, we're going to talk about the 3DGS strategy. And so this is kind of something new that we're implementing. And Professor Lobby and Richard, you guys kind of got the intro to this at the Undergraduate Research Expo. But essentially how this works is we reconstruct the track in 3D space. So we create a 3D scene. And from the Kalman filter, we have an approximate location of where we should be. And with that, we create a bunch of candidate photos. And so that's where the 3DGS comes in. So we'll generate a few candidate photos and match to what we see from the camera. So that's kind of the general idea. And we plan on doing that with a structure for motion strategy instead of just matching images based on pixels or colors, so that we can filter out things like people walking along the track, or if there are slight changes in the weather, for example, that's not going to be an issue. And a question that we have, which if anybody has some insight now or later is also fine, is if you recommend treating the 3DGS localization as soft measurements or hard measurements for the Kalman filter. Okay, yeah, we can also go back to that at the end. So next, the calibration pipeline. So what this does is it just optimizes the cart parameters for the given day. So something like friction can change depending on where you are on the track, depending on which run it is, how many runs you've been doing, et cetera, et cetera. And so that's something that we want to be able to change live so that we can best correct and figure out where we should go. So something to limit issues is that we want to set a, for example, 2% bias so that we don't overcorrect, especially at the beginning. But yeah, we had two different approaches for being able to do this pipeline. And it's either a neural network based approach where we train a neural network on one of the Rubik pies as it's going around. And this neural network will predict if we're overcorrecting, undercorrecting, and then we can make those changes live. Or we can do it algorithmically, so based on the last n time steps, if we're overcorrecting, where should we go, and figure that out. That's kind of a question that we had. And now that this is kind of a pressing issue because we're talking about which simulator we want to use, and especially with the 3D Gaussian splatting, we're looking for some suggestions on simulators that have good cart dynamics. A couple that we were looking at were Carla. Actually, that's kind of what we implemented, but it's not very good. So. Okay. And this is kind of the big system design issue right now. So we have 5 Rubik Pis that I think it somewhat got passed around. Think like a little bit smaller of a Jetson. So compute board, and we want to make a cluster that's on device because one of these Rubiks doesn't have enough compute for what we really want to do. So the question is, how do we do that and not have high latency? Because if we have high latency, we're going to crash. So we do plan on using a gigabyte PCIe switch, which just uses Ethernet. And so bandwidth is not an issue, but latency is. So there's kind of 2 competing options for this. There's using a scheduler, like some fork of Kubernetes, or just using Slurm, which is very light on each node, and distributing the entire code base into tasks. Or we can just hard code it to run on 5 Rubiks, and we can figure out how to do the communication. And this might be less efficient, but it will decrease latency because the issue is latency communicating between nodes. So that's kind of a pressing question right now. Okay. So if anybody has any feedback, questions, things to clarify, that would really be amazing. Yeah, they're passing around the Rubik.
We'll switch back over to having
Yeah.
people